sorry, I pointed.
All right, so for factoring each of these, we're going to see some different techniques for factoring. The first thing we want to look for whenever we're factoring is we want to look to see is there anything I can divide all the terms by. So in the case of number 1, we look at all 3 terms, and there's nothing we can in fact divide all those through by. Having checked that, we then notice that number 1 is quadratic. And we actually do have a way to factor a quadratic. That's the way where we're going to do the add to multiply to and get the 2 different sets of parentheses. And so in each parenthesis, they each start with x. And then we're saying what adds to negative 13 and multiplies to 40. In order to multiply to a positive but add to a negative, they both have to be negative. And so multiplying to 40, the first one that comes to mind is 5 and 8. Well, negative 5 and negative 8 gives us negative 13. So that's a combination. This then is as factored as it can go. So that's factored for factoring a quadratic. Now number 2, again we start by looking at all the terms and see is there anything I can factor out of everything at the start. And in this case, yes. So we say what can I divide 18, 24, and 6 all by? And there's a few different options. We can divide them all by 2, 3, and by 6. Since I always want to pick the biggest one, I'm going to divide them all by 6. So I'm going to start by writing down the 6 and then start the parentheses, because factoring this way is basically using distributive property in reverse. I'm actually pulling the number out of the parentheses. So now I divide everything through by 6. So 18 divided by 6 is 3. I'm not pulling out any x's, so the x to the 4th is going to stay x to the 4th. Minus 24 divided by 6 is 4. And so it's 4x cubed, because again the x parts aren't changing. And then I still have to have this plus here. And when I do 6 divided by 6, I get 1. That 1 has to be there. Oftentimes it can be tempting to forget about that 1. But the whole idea here is that these 2 statements should be equivalent. And if I wanted to check my work, I could check it by actually multiplying that 6 back to all 3 terms. If you don't have that 1 there, there's nothing to multiply the 6 to. And so we wouldn't get that plus 6 hanging on the end unless you put that plus 1. So 6 divided by 6 is 1, so we still include it. All right, now for number 3. Again, I say, can I divide everything through by something at the start? In this case, yes. So in number 3, I can divide everything through by 2. So we're going to go ahead and do that first. So we end up with 2. Then we do 2x squared divided by 2. Well, that gives us 1x squared. And 1x squared is just x squared. Plus, the plus stays there. 26 divided by 2 is 13. That's going to be 13x. Minus stays there. 60 divided by 2 is 30. So now I have that. Now our new wrinkle for the day when it comes to factoring. Number 3 is not done. Number 3 is not done because if you take a look at what's inside the parentheses here, you'll notice it's a quadratic. The stuff inside the parentheses looks a lot like number 1 did. We can still factor this quadratic inside by saying what adds to 13 and multiplies to negative 30. So we're going to do that. The 2 that we factored out at the start, it's going to stay just hanging out front. But we're going to get the 2 sets of parentheses, so it's just going to hang out front of the set of 2. Just like before, they both start with x. We're multiplying here to a negative. The only way to multiply to a negative is if both signs are different. So one's going to be a plus, one's going to be a minus. So then, multiplying to a negative 30, adding to a positive 13, our 2 numbers are 15 and negative 2. Because 15 times negative 2 is negative 30, and 15 plus negative 2 is 13. This then is completely factored. So the new wrinkle that we're going to be heading into with our factoring is we're going to be factoring out the greatest common monomial like we did here in number 2. But then after we've done that, we're going to be able to factor quadratics even further if a quadratic is left inside the parentheses. But again, we only do this if inside the parentheses we have that x squared part. Today we're going to be graphing equations that look like this. We're going to be graphing quadratics that have been multiplied by something. So to start with, about your first graphing grid, write this equation. Y equals 2x squared. Now to be clear about what this is talking about, this is saying we're going to be doing x squared And then once we have that value, we multiply it by 2. We do the exponent before the multiplication. You don't square the 2 here. So when we go to look and see what this graph is going to look like, I'm actually going to bring us back to the very first graph we made of x squared. Remember we made this table? And so there we made the table of x, and x squared was just our y value. But in this case, x squared is not our y. Our y value is actually going to be x squared times 2. So let's start filling that in. I'm going to take each of my x squared values and I'm going to multiply them by 2. So 0 times 2 is, well, 0. Okay, then I'm going to do 1 times 2. 1 times 2 is 2. This is complex math, isn't it? All right, then we do the 4 times 2. That becomes an 8. 9 times 2, 18. 16 times 2 is 32. Basically, we're taking each of the normal y values, whatever we normally go up by, and we're multiplying that by 2 here. That's the effect of that 2 out front. Now, we're going to go ahead and use these data points to graph it. One note before we get too heavily into that graphing. This middle column here, this x squared, nothing there gets graphed on this one. We were just using that so that we could multiply it by 2 to get what our y values really were. We're really just graphing the x and the y values here. All right, so our first point, 0, 0. So that one doesn't change because 0 times 2 is still 0. So notice there already we got something where the vertex doesn't move when we multiply it by a number. Okay, what about if we go over 1? There we got the point 1, 2. Okay, then the next point, is it 2, 8? And then the next point would be at 3, 18. I can't exactly go up 18 on my particular graph and grid though, so I'm not going to worry about plotting that one. So that tells me I can go ahead and jump down and see what happens when x is negative 1, then y is 2. So I can go ahead and plot that one, negative 1, 2. And then right below that we got negative 2, 8. So notice it's symmetrical on both sides of the vertex, just as the other ones were. That's good. It's nice when it's nice and consistent like this. You'll notice all the same rules tend to apply. When we connect the points, we should end up with this shape. Notice it's still that U-shaped graph, parabola. Still the same parabola shape. The only difference is that it's taller because every y value was doubled. We went up twice as far each time. So then when we go over here to describing the transformations, what does the 2 do? Well, you saw something like this before when we did absolute value. When we did absolute value, when we multiplied it by 2, we described it as a vertical stretch by a factor of 2. When we apply it to a quadratic, we describe it as a vertical stretch by a factor of 2, the exact same thing. So that same verbiage that we had when we were dealing with absolute value carries over here to our quadratic. Now, since we're talking about the absolute value though, I do want to bring up something. When we did absolute value, and we saw a vertical stretch by a factor of 2, it told us to go up 2 and over 1. It basically was a slope of 2, or negative 2 on the other side. And it was the same all the way through. But again, the quadratic is a little bit of a different beast. When we're doing a quadratic here, an x squared graph, the slope is not constant. So although we get a few points that do look very similar, it's not going to stay the same over here. Yeah, we go over 1 and up 2, but then we go over 2 and up 8. So that tendency that you had before isn't going to carry through in terms of being able to just keep that same pattern. We're actually going to have to look at the table and think about doubling those x squared values when we multiply it by 2. Having seen how to do that 2x squared, you now can do this. You can graph this equation. So write this equation above your next graphing grid and go ahead and graph it. You know what the 3 is going to do because we just looked to see what a 2 multiplied does. The 4, just for clarity's sake, the 4 does not change to anything else. We don't multiply the 4 by the 3. We don't square the 4 or anything like that. The 4 is going to stay a 4 here. Go ahead and graph it. So when we go and make this graph then, the first thing I'm going to do is I'm going to use the -4, which moves it right 4, just like it did before, and the -8 that moves it down 8. So I'm going to go right 4, down 8, first point there.
What?
And then from that point, we're going to be moving with that vertical stretch of 3, just like we normally would, because that point is our starting point. This is our vertex. It's what everything else is going to be relative to. So from that point, we normally would go over 1, up 1, normally. But in this case, we got that 3 up front. So instead, I'm going to go over 1 and up 3 times as far. So 1 times 3 is 3. So that's where my next point's going to need to go. I go over 1 and up 3. Both sides. Do both sides at the same time. Make your life easier. All right, next up. Normally I go over 2 and up, well, 2 squared. 2 squared is 4, so normally I go over 2 and up 4. The 3 is telling me go up 3 times as far. So instead of going up 4, I'm going to go up 12. So again, I'm counting from that vertex, from that first point I plotted, over 2, up 12, count it out, and in this case you should end up at 4. Okay, what if we went over 3 here? Normally we'd go over 3 and up 9, because 3 squared is 9. Okay, so in this case I'd have to go, instead of going up 9, 9 times 3 is 27, so it'd be over 3 and up 27. Yeah, that's not going to fit. So that tells me that I've now fit all the points that I can for this particular graph on my grid. Draw the curve through them, and you have your graph. Check your graph. Make sure that you have each of the points plotted and that you're drawing that curve in nicely. Remember, it is still a curve. It's not going to be a straight V or anything like that. If you're ending up with a straight V, that's a red flag. It means we've got to check something. Well, when you saw 2x squared, you probably knew this was going to be coming down next. We're going to be taking a look at y equals 1/2 x squared. Yes, we do have to be able to deal with that as well. So, next graphing grid. Write the equation y equals 1/2 x squared above it, and then we'll go ahead and graph that through together. All right, so just like when we did 2x squared, I'm going to figure out what x squared is first, and then I'm just going to multiply it by that number. So before it was multiplying it by 2 or 3. In this case, I'm going to take my x squared and I'm going to multiply it by 1/2. So first point, normally it's 0, 0. 0 times 1/2 is 0, so we still start at 0, 0. Multiplying by a number does not change the location of the vertex at all. All right, then, normally we'd then go over 1 and up 1, because 1 squared is 1. In this case, I'd multiply the 1 by 1/2, and so we're going to go over 1 and up 1/2. Go ahead and do that on both sides of the vertex. Next up, we'd normally go over 2 and up 4, because 2 squared is 4. So, instead of going up 4, 4 times 1/2 is 2. So, I'm instead going to go up 2 here. So, over 2 up 2. All right, next to over 3. 3 squared is 9, so normally I'd go over 3 and up 9. But I got to figure out what's half of 9 here. Half of 9 is 4.5. So we're going to go over 3 and up 4.5 on this one. And we're going to keep going using the same thing. So normally it's over 4 and up 16. 1/2 of 16 is 8. So we're going to go over 4 and up 8. Then if I went over 5, normally I go up 25. Half of 25 is 12.5. That's off my graphing grid. So that tells me I've plotted all of my can here. So then I go ahead and draw on the curve. Check yours to make sure that yours is looking good. Everything's solid on it. All the points and the curve. And then we need to describe this transformation. Notice in this case, I still multiplied our x squared value, so basically how far we went up, by a number. So it's still a vertical, but it's not a stretch. Because a stretch insinuates that something's getting bigger. If I multiply by a number bigger than 1, yeah, it does get bigger, so that's why we call those stretches. But when we multiply by a number between 0 and 1, it gets smaller. And when they get smaller, we called it a compression. So we would describe this as a vertical compression by a factor of 1/2. Go ahead and make note of that with your graph. Write it like next to or on your graphing grid, something like that, just so you can keep track of it. And then to make sure that you have this idea down about dealing with the fractions and to mess with your head, which is always great entertainment, I'd like you please to graph this. Y equals 1/3 x squared. So next graphing grid, write that equation above it and go ahead and make that graph. And so on each of them, again, you're going to take whatever you normally go up by and you're going to multiply it by 1/3. Multiplying by 1/3, by the way, is the same as dividing by 3. That can make some of the mental math a little easier, especially if you're comfortable with your fractions. So let's go ahead and start taking a look at where these points go. First of all, of course, 0, 0, still the same. But then instead of over 1 up 1, we're going to go over 1 up 1/3. So that's going to be just below 1/2 on both sides there. Okay, over 2. Well, over 2 is normally up 4. So then what's 1/3 of 4? Well, that would be 4 divided by 3, or 4/3. 4/3 is 1 1/3. Being good with your fractions, it's going to make your life easier on some of these kinds of things. And yes, they'll keep coming up as time goes on, so keep at it. All right, then over 3 is normally up 9. What's 1/3 of 9? 3. That's a nice easy one. Thank goodness, right? So we go over 3 and up 3 on both sides. Okay, next up, over 4. Normally over 4 is up 16. 16 divided by 3, well, that's 16/3. Turned into a mixed number, and you should get 5 and 1/3. And so we put our next point at 4 and 5 1/3. And we can keep going with those. So over 5 is normally up 25. 25 divided by 3 will give us 8 1/3. So we plot 8 1/3 on that one. And then if you can fit over 6 and up 12, you'd fit that on too. Because 6 squared is 36 and 1/3 of 36 is 12. But your grid may not have included that. So this is what your graph should be looking like. Check each of the points, check the overall shape, make sure everything's looking okay. Yeah, 1/3 can be a little awkward to work with, but outside of the awkwardness of some of the weird numbers we get, hopefully we can still work with it okay. We still should know all the rules and stuff that would go with it. Then we're going to do one last graph together. We're going to put all the pieces together and graph this one. Y equals 1/2 times quantity x minus 5 squared minus 4. Go ahead and graph this on your own paper, and remember to include the equation with your graph. Because a graph without an equation, when you go back and look at it later, is not at all helpful. All right, now check and see how you've done on making your graph. This is what your graph should end up looking like. Yes, you still go right 5 and down 4 to get to your vertex. And then it's just the ups from there that we're cutting in half. And then once you've checked your graph and made sure it's all looking okay, please then also with your graph there on your paper, list out the transformations, list out the coordinates of the vertex, give the equation for the axis of symmetry, and give the range as well, please. And then check and see how you've done with those. So amongst the transformations, the 1/2 is a vertical compression by a factor of 1/2. It's a compression because it's between 0 and 1, so it makes it smaller. The minus 5, it's in with the x, so it's the opposite, and it goes in the x direction, so that is indeed right 5. Then the -4 hanging on the end, that goes down 4. So we list all those out separately. Then your vertex, just give the coordinates of the vertex. Axis of symmetry. Remember that the axis of symmetry is that vertical line that passes through your vertex. And so we're actually giving the equation of that vertical line. That's why we have to have the x equals in it. Without the x equals, it's just a number. The x equals makes it a vertical line. And then finally, the range, y greater than or equal to -4, because the range is a description about which y values are included on the graph. And so in this case, you can see they start down at -4, and then all the y values are above it. So that's why it's greater than or equal to.